Good morning. Today we're gonna continue on chapter 8. We're gonna solve a couple more examples. Remember last time we did the integral, double integral, and also the triple integral. Today we're gonna start doing some numeric differentiation. So we'll start with the polynomial differentiation, and then we'll move to a start solving differential equations, first order and second order differential equation using the ODE45 command, and also we're going to use the LTI commands as well. So yeah, let's start. Let me share my screen here, and let me pull this. So I'm going to start with this problem, problem 22. We have two polynomials. First, P1 is 5x squared plus 7. P2 is 5x squared minus 6x plus 7. What we want to do, we want to get the derivative of that second polynomial, and then this is the A. B, we're going to get the derivative of the product of these two polynomials. And C will get the product of the division of P2 over P1, no, derivative of the division of P2 of over P1. So let's do that, and we'll start. Yeah, let's do this one here. So let's start a new script. Let's do this one here, and we'll start with defining P1. P1, open in brackets. Again, it's 5, 0 because there's no x, and 7. And P2 will be equal to 5 minus 6 and 7. Okay, so close the bracket and suppress that. We'll start with the derivative of 2, which is for polynomial 2 is equal to poly derivative, so poly DER of P2, right? So P2, and so we want to get that. So that takes care of part A. Now the derivative of the product, so we're going to say product is equal to poly der of P1 and P2, right? And for the last one, we're just going to do the numerical numerator and denominator. Close the bracket is equal to poly derivative of P2 P1. Okay, so I close the bracket, and I'm going to call this save as 918. So go down in here. Yeah, 922 here. Here. Save, and let's run this here. So let me maximize this to see what we mean by that, what we mean by this solution here. So the first one, derivative of P2, if you really want to write it down, so derivative, so D P2 dx, in this case, will be equal to 10x minus 6. So that is A. B, B, you're talking about the product. So for part B, D P2 or P1 P2 dx, and that should give you 100 with x cubed, right? minus 90x squared plus 140x minus 42. Okay, that's how I will need you to write this if it is a homework, or if it's a quiz or an exam, you need to write it in this. The last part, which is P2 over P1 dx, you're going to get Q, the numerator will be equal 30 x squared minus 42 divided by 25, in this case x4, 25 x4, if you look here, 0x3 plus 70 x squared plus 49. Okay, this is the numerator and this is the denominator. All right, so that's straightforward. Use the Pauli derivative for all of these. All right, so let's move to the second problem. Second problem, this one here. So in this one, I'm going to do this in a couple of ways. I'm going to do that using the ODE45 command. So let's do this. Plot the solution of the equation. This is a first order differential equation. If f of t equal to 0 for t negative, and ft equal 15 for t positive. And the initial condition for this would be y of 0 is equal to 7. So this is again, it's easy to solve. We're going to solve this and plot these in 3 different ways, but we want to always when you want to start, if you want to use the ODE45 command, there's one thing that we want to do. Always you want to establish a function, and then you have to call the function in the ODE45 command. So again, we're going to do that also when we do the LTI command as well. All right, so the first thing I want to do, just want to put everything as a function of y dot. So y dot will be equal, in this case, ft minus y over 6, right? So for the first, I'm going to try to do this for this one here, and then we'll do the other one. So let us go in here and start establishing a new function. So let's do a new function here. And the new function is I'm going to call this function y dot is equal to, I'm going to call this equation P9 to 4, okay, equation for problem 9 to 4, and I'm going to equation of problem 9 to 4. The domain for this, I'm going to choose from 0 to 24 for t, and we can change that later. We'll see if this will work. If it doesn't, we'll change it. And 7 will be the y0 right there. Y0 is 7. And just close so it is y dot. Actually, I don't have to do this solo. So let me first 9 to 4. Let me just define the equation before we do the initial conditions. So let's define the equation, and then I call it with the ODE45 command. So let's not get confused here. So that is the name of the equation, and what I want to do is it has to be a function of t and also y. So that is the function. Let me do the function y dot is equal So y dot in this case, yeah, y dot is ft minus y over 6. I don't know where that, yeah, right there. No wonder it disappeared. Okay, so that is y dot ft minus y over 6. All right, so in this case, y dot is equal 15 minus y over 6. That's right. All right, so let's suppress this and end that function. Save it. Yeah, save as. It's going to give me that function. I'm going to just save it. And I'm going to open a new script, and I'm going to do the ODE45 command. So T, Y equal ODE45. And now I call the handle function, and that way it's a problem or equation in E924. That is equation for problem 924. So I call that equation, and let me now do the t-span. So that's from 0 to 24, and then I'll assign the boundary condition or the initial condition, which is 7, and close the parentheses. Let's press it, and then we'll do here plot ty, and then just x label t, and also y label y. Okay, so we have that. And let me save this one here. Save as. Change this one here. B for A. So save it. And now what I want to do is just run this. So if I run this, I will come up with this plot, which is y versus t. Okay, so that is the solution of this differential equation. So let's regroup here. When you use the ODE45 command, the first thing you want to do, you want to define a function. And that function, you're going to call it in the ODE45 command with the time span that you want, or the x-axis, whatever you're trying to plot, and with the initial position, condition. Now, the initial condition in this case, you have only one initial condition because it's a linear first-order differential equation. Where in this case, you have the, for example, y of 0 is equal to 0 or equal to 7. If it is a second-order differential equation, which is going to solve something like this in a minute, you're going to probably have two initial conditions, y of 0 and y prime of 0, which is the derivative of y. So let us see if ft equal to 0 instead, how this will fare. So if we go back to the equation, let's go back to the equation, and what is that here? That equation here. And remember, it is 15. Let's suppose this is just 0 here, okay? And let's save. And let me call back the equation problem, this one here. And let me run it now, and let's see what we get as far as figure. So you'll see when we change the initial condition, it changed the behavior of the function. Okay, so or the step functions for that, because f of t is 15, and when f of t is 0, look at the response, how will change. All right, so we'll do one problem where we'll change also the initial condition in a minute and see how it affects our result. But for now, we're just changing ft and see the response of that function, how it will behave. Oh, the same problem, what do I want to do? I wanted to solve it using a different method. So I want to solve it actually using the, again, LTI method. But the way I want to do that is want to define first the system equation. So how are we going to do this? We are going to, let's look at the equation in here, going back to this equation. So we're not changing this equation, and we are going to set y to be equal to 1. And the reason why we want to do that, because we want it to be in this manner. So let's see how we can do that in just a minute. Let me minimize this. And all right, I'm going to actually pull this from, just to remind you of these equations that we want to use, the LTI equations. All right, so this one here. I'm going to use the first command, which is the system command. I'm going to specify this, but I want to look at the equations and see and find what A and B are. So dx dt is equal to ax plus bu, and y is equal to cx plus du. Remember, y will be the output for x. So in our case, because it is one ordered differential equation, linear differential equation, we'll be able for us to just set c equal to 1 and d equal to 0, because all we're looking at is one output, which is the y variable. So dx dt in this case, we have x dot, we have y dot is equal to, again, as of a is the matrices in this case, plus, but in this case, because it's only a 1 degree linear differential equation, it's going to be only one value. But if we have a second degree differential equation, which is going to solve later on, it will be actually a matrix that we have to insert, plus b u. So let us do that. So going back in here, in this case, I'm setting ft for now to be equal 1, because I will change it with the step. Because remember, he said ft could be 15 or it could be 1. So in this case, y dot in here will be equal a times y plus b times f. Okay, And so in this case, A will be equal, if you look here, will be equal minus 1/6, and B will be equal 1/6. And so let's do that. Yeah, let's do this one here. So we're done with this. Let's start with a new function, new script. And so we're going to say system here is equal to SS, and you're going to open a parentheses, and you are going to put the value of A. In this case, A will be equal minus 1/6, so minus 1/6. And then you're going to do B. B in this case will be 1/6. And you can put 15/6 if you want, but then you get you don't have to do the step response. But we'll see why you want to do 1/6, because that will really help a lot. You do as a unit step, and then you multiply it by 15, and you see the response. And again, we said C will be 1, and D will be 0. And then close that. So that defines our LTI system function. So that's done. We move to T. Let's open an array of T. Let's use the line space function. And we're going to do from 0 to 24. Now, when you do the LTI commands, you really want to do the time. You want to create your array. If you do the ODE45, you don't have to, because it will just put the span of that you want, and it will automatically give you the increment. Here we're just going to do 1,000 increment, and also suppress it. So now we want to do Y1 of T. So that is the first response. We want to do this for a step function, and that step will be 15. Remember, f of t is 15, so I'm just going to do 15 times system, right? And also t. So that will give me the first response, step response, and the second one will be y2 t, and I'm going to do the initial. When you do the initial function, you have to specify the system, and also you want to specify the initial condition. The initial condition, y of 0 is equal to 7, so you're just going to do 7 and also t, and then close that and press that. And then you're going to just plot both of them, because you want the initial response for the system, which is y, and also you wanted the response, the step response when y or ft is equal to 15. So we're going to plot t, and we're going to add y1 plus y2, because that will give us the response. Sorry, y1 plus y2, and close it. We're going to x label. We're going to do this t, and y label. We'll do this one y. Okay, so let's save that, and we are going to call it. Do this one B, and just save it, and let's run it. So if you run this and go back to the figure, you'll see that you get the same distribution for y, and it gives you the same thing. We didn't have to establish a function in this, but again, you have to do the step and you have to do the initial if you want to get the whole thing, the whole response. Another way of doing this, if you really want to solve this problem, so if you want to solve, if you set y equal to, yeah, let me do this one here. If I set y equal to 15 in here. So again, y dot will be equal to, that will be y dot, right? If you want to solve for this equation, if you want to solve for this differential equation, the exact solution will be equal y will be equal to 7e minus t over 6 plus 15 1 minus e minus t over 6. Now, I'm not going to go over how I did this. This is a math problem. This is a linear differential, ordinary differential equation. When you have the first order of a function is somehow a function of the function itself, then you're gonna expect that it is an exponential function. So there's a solution for that. What I'm gonna do, I'm gonna just plot y and see if it agrees for what we did for in the previous two sections of this problem. Remember, they used the ODE45 and we use the LTI command. So let's go back and so let's minimize that one and let's start a new function. And all I'm going to create an array of t. So let's do that. T equal, I'm going to start with 0, do 0.005, and again 24, suppress it, and then we're just going to put this equation. So y is equal to 7 times exponential of minus t over 6, right? Plus 15 times exponential or 1 minus exponential of minus t over 6. Okay, close this and yeah, close it to here. And then suppress it. So y here here 7 times exponential minus t over 6. So you always have to do not want to miss any parentheses in there. Okay, so that's it. Let's plot the ty and let's x label t and y label y. Okay. Y label. All right, so that is it. Let us also save this one as part C. I'm just expecting to have very similar distribution. So see here, save and just run. So if I do that, I go back to the figure, you'll see that I get the same curve for y. All right, so we did it 3 ways. When you do the ODE45, you need to establish a function. You call this function in the ODE45. You find the span of time in this case, and also the initial conditions, and then you can plot it. And remember, on the ODE45, it will give you a column. If you are solving if you are solving a first order differential equation, you're going to get only a set of solution in one column, which is this function itself. If you are solving a second order differential equation, it's going to give you 2 columns, and each column, the first column will give you the y arrays, and the second column will give you the y dot. okay, because it's going to solve for the first derivative and the function of, because you have a second order differential equation. And we're going to solve the problem. This following problem will show us how to do that. So let's minimize this and let's move to this problem. So following equations, this is problem 32. So the following equation describes the motion of a certain mass connected to a spring with a viscous friction on the surface. The equation is 3y double dot plus 18y dot plus 102y is equal F of t, where Ft is an applied force. Suppose that F of t is equal to 0 when t is negative, and F of t is equal to 10 when t is positive or equal to 0. We're going to plot y of t for initial conditions. Y of 0 is equal to 0 and y dot of 0 is equal to 0. Then at B, we're going to change those initial conditions and see how this will change our results. Okay, so the first thing that you want to do, I'm going to use the ODE45 command. You can use the LTI because you're still dealing with linear equations, so differential equation. So the first thing I want to do, I want to do some renaming in that equation. And remember, always you wanted to do as x dot. So the first thing, let's call x1 here, x1 to be equal to y, and x2 to be equal to y dot. Okay. Now, if we do that, then x dot 1 in this case will be equal to x2, right? And so that is the first equation. And the second equation, I'm going to bring it from here. So that is the first equation. And the second equation is going to give me 3. Let's do that here. 3. Y double dot will be equal x dot 2, right? X dot 2 plus 18. Y dot will be equal x2 and plus 102. Y will be equal to x1, and that is equal to f. Now all I have to do is just to put everything as a function of x dot 2. So that's going to give you f of t. So let's just put 1/3 in here, and that's going to give me f of t and minus 102 x1 minus 18 x2. Okay, so this is equation 1 and this is equation 2. Right, this one and this one. And as you can see, this is x dot 1 and this is x dot 2. So now we're ready to do, remember it's ax plus b, right? It's it's in that order, ax plus b. So again, x dot is equal to ax plus b, in this case, f. In this case. Right. So, but ft in this case will be given to 10. And the second time will be equal to. So that's a. All right. So let's go to MATLAB, and that's the first thing, because we're going to use the ODE function. The first thing we want to do, we're going to establish a function and save it. So let's do this here. This one here. So get a new script, and so A in this case, just before I move here, so I'm because I want to define A here. So A, if you look at these two functions, the first it is 0, right? Because x1 is 0. I'm looking at the first function here, and 1, right? And then you have x1 here is minus 102 over 3, and x2 here is minus 18 over 3. So that is A. And B in this case, what is B? Will be equal to 1/3, right? 0 and 1/3. So the first equation would be 0 and 1/3. Okay, these are the matrices. So let's start by doing function here. All right, so let's just do the function here. Function, and we're going to do x dot equal problem P932 P932. So that is the name of the function, and I'm gonna do this t and also x, right? And A, we just find out what A is. A will be the first matrix, which is 0 and 1. Second row will be minus 102 over 3, and the minus 18 over 3. Close B will be equal to 0 and 1/3. All right, so that is A and this is B. 0. Okay, so we're ready to put the equation. So x dot is equal to A times x, right, plus 10 times B. Remember, f of t is equal to 10 in the first case, 10 times B. All right, and then just end that function, save it. Save it the same name, don't change that. So now I'm going to open new script and I'm going to call this function in the ODE45 command. So we're going to do x and t, or t and x. So t, x, and you just have to be equal, ODE45, ODE45, in the parentheses, and you're going to call that problem, or that function problem. What do we call it? We call it problem P932, and so that is the function that we're calling, and we are going to define the span. So we're going to define the span of the time. You don't have to put the increment, or just put initial and final. It will actually do that for us. It will choose a very minimum small span to plot. And here where we're going to put we're going to insert the initial condition. And the initial condition in this, if you look at this problem, the initial condition is, oh, this is really messy. So let me open this here. So initial condition, the first one is y0 equals 0 and y dot 0 equals 0. And in B, we're going to change, we're going to set y dot 0 equals 10 and see the difference in response. So yeah, let's do here. So let's just do here 0 and 0. Okay, 0, 0, and close it. Close the parentheses, and that should be it. And then I'm just going to plot, you know, I'm going to do plot T, and I want to plot first only the displacement, or y. I do not want to plot y dot. But if I put just x, it's going to give me two plots. So I will come back to this in just a minute. So I'm going to plot the first column. So so it will be sorry, that's a column, and we are going to do 1, right? Because that only the first column, which is y. And so let's close that. And then we're just going to do X label, right? And X label, we're going to do this T. Okay, and we're going to do Y label, Y, right? So that's what we're trying to plot. And let me save this, and bear with me here in a minute, because it's very important to understand this. Let's just do this one here, P here, right? So that is P, problem P 932. Save it. So that is 932. Save that. So let's just do here 932. Save. Okay. So we have 932 in here, and let's run this. Okay, something is not there in problem P line 1. What did we do wrong here? Problem P, ODE45. Did I call the right function? Let me just make sure. Problem P932. Yeah, it is a function. It's correct. Something that I did that is just define function or variable. Problem 932, line 4. All right, let's just do this one here. Line 4. Oh, so that is what it is. Save and let's see. And let's just go back in here and run it. Something is not right here. With the EP span YZ option. So we got this correct. So 0 to 2 and 0, 0, ODE45. So we open the bracket, add problem P 932 from 0 to 2, 0, 0. That's still giving us the same problem with this one here. So X dot. All right, so that is the problem, because that matrix, you need to put a semicolon in there because it's a 2 by 2 matrix. So I believe that is the problem. So let's do that, and let's run this one now. Okay. So well, I did not want to do the X dot and Y dot, so let me go back in here and let me just do this like that. Press it. All I want to do is just want to see the plot. I don't care about those numbers. So let's run that. So we go to the figure, and that will be the Y response for that. So I had a problem with that matrix. Always you want to make sure you separate those rows with a semi-column. Now, this is the Y. We're doing the Y plot. If you want to find the velocity Y dot for this, all you have to do is just to you go in here and change this to 2, because remember when MATLAB used the ODE45, it's going to give you, because it's a second order differential equation, it's going to give you the solution for Y and solution for Y dot. The solution for Y will be located in the first column, and the solution for the Y dot will be located on the second column. So if we want to do that, and we're just going to have to do here Y dot in there, because we want to actually see how this velocity is behaving. So if you do that and you look at the figures, you will see that this is the behavior of the velocity. If you, for any reason, if you decide to plot both of them at the same time, but you have to make sure that you do the legend for that, all you have to do is just do Y here and Y dot, for example, and just this and just plot T versus X, and if you just hit that, it will give you two plots on one. Okay, and again, this is Y and Y dot, so you can plot all of them, and definitely you have to use the legend to see. You know, for your information, and this is every time if you're doing a third degree differential equation, you are going to expect 3 sets of solution in 3 columns, which is going to give you the function itself, Y dot and Y double dot. Because we're just doing a second degree differential equation, you are going to get 2 sets of data, Y and Y dot. Okay, so I think what I'm going to do, I'm going to stop here today, and maybe what we'll do, maybe if I can solve this one, you know, before we do this, I just want to make sure that you understand. Let's go back and do the X. Yeah, let's come back in here, and I'm just going to do the Y only, and so the Y will be 1 in here, and close the bracket, and let me get rid of that. I want to see the effect of changing. Remember here, this is if you look here, a Y dot here was 0, but now I want to change it to Y dot 0 equal 10. So if you do this, let's run this before we change it and look at the response. So if you look at this figure, that is the Y response. If you change this, so if you look here, let me just minimize this. If I change that to 10, okay, and that's exactly what he's asking in B. You see the response, and then if you run it, you'll see the response is a bit different. Okay, So every time you change the initial condition, if it is the derivative or the function itself, you will have definite different you're going to have a different types of results or plots that you're going to have. Now you just have to be careful with that, how you're going to solve this one here. So maybe the second problem that we do, yeah, let's just do the this one, so that should be fine. ODE45. You know, let's do this one, the same one, using the LTI methods. Okay, so since we are still working on this one, we're going to use the LTI method. So one thing that you want to do is let's where is that error? Let's see here. So let's do this, and let me wipe all of these here. Right, I want to use the LTI method to solve this problem. So how am I going to do that? I'm going to look at the equation in there, and I'm going to use the transfer function. Now, what is the meaning of a transfer function? If you guys took control, I don't know who control systems, who taught this, I know that Dr. Who used to teach that, Dr. Oren, I'm not sure who was teaching it, but control system, you deal a lot with transfer functions. We use also Simulink, as you can see, but control a transfer function represents the behavior of any system, if it is dynamic, or electrical, or it's actually the description of the behavior if it is a mechanical problem of the dynamics of the problem. And that transfer function, it is, you know, to me, I describe it similar, or if you can draw the parallelism, as a stiffness matrix and a finite element, because it describes the structure itself. It describes the system itself, how it will react based. If you have a transfer function and you give an input or a step input, you see how this will affect the behavior. If you, for example, on a plane that's flying, if the wing or the aileron has a transfer function, the elevator has a transfer function. So any step function or step input that you put, it's going to actually give you a response. So transfer function describes the mechanism or the dynamic of any problem. So when you want to use it using that transfer function and solve it and see if will help us. And if you go back to the command, I'm just gonna show you that system is equal to TF transfer function, the right components and the left components. So you're gonna separate the right components will be usually as a function of that input function ft in this case, and the left will be in this case x or y, x double dot, x dot, and x. So you want to pick up those coefficients from the right and from the left and put them in that parentheses. So in our here, you get in the right, you have only one coefficient, which is 1. On the left, you have 3, 18, and 102. So let's do that. Let's go to, yeah, let's revise this. and pick up this one here. Let's do a new one here. And let's start with the system is equal TF transfer function, open parentheses. And again, we said on the right will be 1, and on the left will be, what is in the left is going to be the 3, right? 18 and 102. Okay, and close that, and close the transfer function and suppress it. And then we'll do yt, and is equal to, we're going to do the step function. And remember, it's telling us that ft equals 10 right here. F of t is equal to 10, so we'll do 10 times 10 times system, that's transfer function, and again suppress that, and then we're going to do plot ty, and then again x label t and y label y. Okay, so and then we'll see how. Let's save this. Save as. We're gonna call this 932, and I'm just gonna call this B. Save it, and let's run this. So if you look here, you will see that also we get the same behavior of that plot, same results. Okay, so we used the step, and you get the same thing for that transfer function. So again, you change that. Remember here, n equals 0. If you change this to be equals 0, so if you do 0 in there, you will have different type of behavior, different type of function. Right? So that's one way of doing this. So transfer function, you have to put the right coefficients, and then you do the left coefficients, and then you just call it YMT. Step function in this case 10. So if you, for example, you do this as 0, for example, let's do that. This one's 0, and then run, and you'll see that you have a 0 Y in this case. 0. There's no. It doesn't give you any curve. So, but now for 10 will be equal to 10. Right? So you run it here, and then you'll get that behavior. Okay, so I think we'll stop here today. Next time we'll do this, the unit step response for this. We'll do these 43 also, a couple more, and then hopefully we'll start chapter 9. Yeah, just work on this on your own. Try to do this in both ways. Do it using the ODE45, and also use it during the LTI function, if it is transfer function, or if it is step, or if it is the other functions, the SS functions. So you go back in here, and you see there's SS function, there's TF functions, and also you can do the initial, and you can do the step response. All right, I think we'll stop here today, and we'll continue next time. Thank you very much, and we'll see you in the next lecture. Thanks.